Hello, our viewers. Previously on our discussion, we have tried to revise the main points concerning on oscillations and waves. We have tried to define the main terms like cycle, period, frequency, amplitude, simple harmonic motion, damping oscillation, and so on. And today we'll try to discuss about waves optics. What do you mean by wave optics? First, we'll try to see the term wave optics. Wave optics is a branch of physics which mainly concerns the study of nature of light. Actually, there are different theories concerning on the nature of light. Since the era of Greek philosophers, light is considered to be particles. Sometimes they are considered to be only have a wave nature. So among the different theories proposed on the nature of light, the common are wave theory and corpuscular theory, as well as the quantum or the modern physicists theory, known to be the quantum theory. So according to wave theorists, they consider the nature of light as a wave nature only. Corpuscular theory tries to propose that the nature of light appears due to the particle nature, whereas the quantum theory finalized that it has both wave and particle dual nature. That's what it says. So wave theory was first proposed by Christian Huygens, and he tries to explain all the four properties of waves like reflection, refraction, diffraction, and interference using a wave nature, or it is explained due to that it is a wave nature. Whereas corpuscular theories tries to explain mainly the reflection and refraction of light due that it has a particle nature. So we'll try to see these one by one. First, to understand the concept of these theories, first we should have to know the main terms under these units. Here we have wavefront and ray diagram. These are important terms. What do you mean by wavefront? First, let's try to see what do you mean by wavefronts. Wavefronts are a set of points or a locus of points of having the same phase. Suppose here you have a wave. It might be a spherical wave, or there might be a planar wave. Suppose that it is a water ripple, so that there will be a series of concentric circles, so that some will be rising up. For example, if you try to see the section view of a water ripple, there will be higher and downward, upward and downward. The upper point is known to be the crest, whereas the down part is known to be the trough. So it's possible to observe it from top view, so that this might be the crest, this might be the trough, this might be the crest, and the broken line represents the trough. So these points are set of points of having the same phase, because all those points are found on the crest. All those points are found on the trough. These points are all found on the crest, whereas these one are found on the trough. Therefore, wavefronts are set of points or locus of points tries to represent particles or having the same waves, having the same phase. This is known to be wavefronts. So there can be a spherical wavefront, or there can be a planar wavefront. For example, here you have a plane, so that this might be the particles found on the crest, whereas this one are the particles found on the trough. So that crest, trough, and so on. So these are known to be wavefronts, a set of points of having the same phase. Whereas ray diagram is a diagram used to represent the direction of a wave. In which direction does this wave propagates? Does it propagate to the left, to the right? So that it is represented using a ray diagram. In this case, suppose that the ray is acting on this direction to the right, so that this wave is propagating to the right. And here we have a spherical wavefront, so that we can have a ray diagram. And one thing, very important thing, is ray diagram and wavefront has mutually perpendicular, so that this is the wavefront and ray diagram are perpendicular to each other. The same is true. For example, here you have a spherical wavefront. At the point of contact, there is a point of tangency, so that the tangent line and the ray has a perpendicular to each other. Therefore, generally, we can say that wavefronts and ray diagram are mutually perpendicular to one another. And the other point is the distance between two consecutive wavefront, for example, from crest to crest, is known to be wavelengths, or it's possible to take from trough to trough is known to be wavelengths. We know that wavelengths is the minimum distance between two corresponding points of consecutive waves, so that you should have to recall these points. So these are the main terms, wavefront and ray diagram. Now let's try to see those theories. The first theory is wavefront. Wavefront was proposed by a Dutch physicist known to be Christian Huygens. So Christian Huygens proposed that the nature of light, like reflection, refraction, diffraction and interference, is due that it has a wave nature. Actually, while he was alive, he was trying to explain about reflection and refraction, but the other one, diffraction, interference and so on, was proposed by the wave theory supporters like Thomas Young, Augustin Fresnel and so on. Therefore, we'll try to see this theory. So Huygens proposed principles, and this principle is known to be Huygens principle, and this principle is very important to explain how does a light propagates, and it is very important to apply and prove the law of reflection, refraction and so on. What is the Huygens principle states? There are two statements of Huygens principle. The first statement states that points on the primary wavefronts are the source for the secondary wavelets. Here, wavelets are very small spherical wavefronts. Very small spherical wavefronts are known to be wavelets. Therefore, suppose here you have a primary wavefront. On this wavefront, we have different points of disturbance. We know that waves are formed due to disturbance of particles. So if you take these particles, each particles will produce their own spherical wavefronts, okay? And this particle as well produce its own wavefronts. And at this case, for example, let's take these and these wavelets. Those wavelets here and here, they are going to cancel one another because they are out of phase or antiphase, so that the only thing left is here. So that there will be another wavefront produced. Again, points on these wavefronts are the source for the others or secondary wavelets. So the first statement states that points on the primary wavefronts are the source for the secondary wavelets, and the secondary wavelets, those spherical wavelets, are moving with the same wavelength, with the same frequency and speed as that of the primary wavefronts. So the primary wavefronts and the wavelets, the secondary wavelets, have the same frequency. So that keep in your mind, and it's very important law to prove the law of reflection, refraction and so on. Here, let's try to see some of the properties of waves: reflection, refraction, diffraction and interference, as we have previously discussed under oscillation and waves. The common properties, these are the common properties of all waves. Light as a wave has reflection, refraction and diffraction, as well as interference. So reflection means the rebouncing of light from a given boundary. There might be a source. From that source, here you might be having a source, it might be sunlight. From that, here you have a mirror or any obstacle, so that it might be rebounce. This is a regular reflection, whereas this one is irregular or diffuse reflection. So whatever, there is a source and there is a boundary. The light which is reflected, which is rebounced from the boundary, is known to be reflected wave. So light can be rebounds back, so this is known to be a reflection. It's a well-known nature of light. Now, we are going to apply Huygens principle to prove the law of reflection. The law of reflection states that if you take one of the light, for example, from among the incident rays, the incident rays are rays from a source, whereas reflected rays are rays from a reflected surface. Therefore, if you take incident ray and reflected ray, there is a law. Incident ray, reflected ray and normal line are coplanar, and the other law says that the angle of reflection and angle of incidence and angle of reflection are equal. This is what the law of reflection says that. And it's possible to apply Huygens principle to prove reflection. So it's a mathematical approach that we are going to follow using a similarity of triangle. It's possible to apply and prove that Huygens principle obeys the law of reflection. Okay, it's possible, and you can find it in your physics textbook. So it's possible to use a mathematical approach, similarity of triangle and congruency of triangles. And the other property of light is refraction. Refraction is the bending of light as it travels from one medium to the other medium due to the change of speed. For example, here you might see a glass and here you have a straw. The straw seems to be broken due to that the light itself, the information tailored to our eyes is light. So the light is bending and it tells us that it seems that the straw is as well bends. Therefore, this property of light is known to be refraction. So light refracts or bends as it propagates from one medium to the other medium due to the change of speeds or due to the change of speed of light. And in this case, for example, let's take two medium, here air and glass. Glass is more denser than air. So as light propagates in air, it will have a rectilinear or straight motion. If there is no glass, actually the light is going to have its own straight motion. But suddenly it faces glass, more denser particle, so that the light is bending towards the normal line. Here you have a line which is perpendicular to the surface. So as light propagates, if it is a uniform medium, it will propagate straightly or rectilinear motion. But now there is a denser medium. As it faces a denser medium, it bends towards the normal line. Or if you reverse in the other direction, for example, if it is moving in the glass, then in air, then it will bend away from the normal line. If it's moved from the less denser medium to denser medium, it bends towards the normal line. As it moves from denser to less denser medium, it bends away from the normal line. This is the property of light. And we do have a law of refraction. As previously we mentioned that there is a law of reflection, so that the angle of incidence and angle of reflection are equal. But here we have also another law known to be the law of refraction. In this case, for example, if you take this incident ray and forms like this, if it is a uniform medium, it will propagate rectilinear motion. But it faces a more denser medium, so that it bends towards the normal line, and the angle here, the angle of incidence from the normal line is relatively larger. Theta 1 is greater than theta 2. Why? Because it bends towards the normal line. So the law of refraction states that sine theta 1 over sine theta 2 is equals to the speed of light as it propagates in medium 1 and the speed of light as it propagates in medium 2, the ratio of their speed. And one thing, very important thing is, for the same time interval, as the light propagates in different medium, the frequency remains constant. For example, here if there are 4 waves within a second, then again when it propagates in this medium, there will be 4 waves within a second, so that the frequency remains the same despite the change of velocity. The velocity in medium 1 and the velocity in medium 2 might be changed, but the frequency remains constant. We know that velocity generally can be given as, or speed of waves can be given as lambda times frequency. If the velocity changes and if the frequency remains constant, the wavelength also changes. So as medium changes, the velocity or the speed of the light and the wavelength changes, but the frequency remains constant. Therefore, keeping this in your mind, V1 can be given as lambda times lambda 1 times F1. V2 can be given as lambda 2 times F2. In this case, frequency 1 and frequency 2 remains constant, even though there is a change of medium. So keep this in your mind. It's possible to have V1 over V2. Instead of V1 over V2, lambda 1 frequency 1 over lambda 2 frequency 2. Frequency 1 and frequency 2 can be cancelled out because they are equal. Therefore, it's also possible to represent the law of refraction using lambda 1 over lambda 2. As well, it's possible to use refractive index. Refractive index is a correlation factor, and it is tried to correlate the speed of light in vacuum over the speed of light in a given medium, so that it's given to be c over v, where c is the speed of light in vacuum, and it's 3 times 10 to the power of 8 meter per second, and v is the speed of light in a given medium. It might be water, it might be glass, or any other medium, so that refractive index is always greater than 1, because the fastest thing or the speed of light is faster in vacuum, and it is the fastest thing in the universe so far. So it's possible to use refractive index instead of using velocity and wavelengths for the law of refraction. Sin theta 1 over sin theta 2 can be given as V1 over V2. So if you use refractive index can be given as C over V1 for medium 1, and refractive index of 2 can be given as C over V2. This is known to be Snell's law. And it's possible to apply Huygens principle to prove the law of refraction. Okay, it's possible to prove the law of refraction using Huygens principle. And again, we should have to follow mathematical approach and similarity of triangles to prove the law of refraction. You can find it on your textbooks deeply, so you can see that. And now let's try to see the other law, which is known to be corpuscular theory. Corpuscular theory was proposed by Sir Isaac Newton, and it states that nature of light, like reflection and refraction and so on, can be explained due to that it has a particle nature, and it states that light is made up of a very tiny particle known as corpuscles. Tiny particle, it means in Greeks, corpuscle means tiny particle. So that those particles are the one which enables light to have reflection, refraction and so on. Therefore, he tries to explain reflection as there is a repulsive force between those particles, the particles of the light known to be corpuscles, and here you have a reflective medium. It might be glass, so that the particle of the glass and the corpuscles has a repulsive force. We know that Sir Isaac Newton is somehow related with force, so that he tries to explain the reflection of light as a repulsive force between the particles of light, corpuscles, and the reflective medium. The other thing is different colors formed on our retina appears due to that corpuscles have different size. So different lights from sunlight appears different colors. Those colors are due to the difference in size of the corpuscles. This is how he reflects, or this is how he replies. And refraction is due to the downward accelerating force. This is what he proposed. There is a downward accelerating force, so that those particles, the corpuscles, are moving more faster in a denser medium. This is what he says. But unfortunately, this theory is failed, because that light is moving less faster in a denser medium. It's not moving more faster in a denser medium. This was later explained by Augustin Fresnel, Jean Foucault, and Thomas Young as well. Tries to answer the question of corpuscular theory, and this theory is actually a failed theory, so that you can see this. And now let's try to see the other properties of light. So far we have tried to see reflection and refraction. There is also diffraction and interference. Diffraction means the scattering of light as it faces obstacle, or the bending of light as it faces obstacle around the edge. There is a tendency or a property of light to bend around an edge, or any waves. Okay, actually not only for light, but it's very clearly possible to see that sound wave or any other wave can bend around a given obstacle. Here you can have a gap. For example, you can have a planar wavefront. As you face a gap here, there will be a scattering of light. This scattering of light is known to be diffraction. We call it to be diffraction. And diffraction is more visible for larger wavelengths. Even though the gap is larger, it's possible to observe that. But for waves like sunlight has a very short wavelengths. For a very shorter wavelengths, the gap should be very, very small, so that we can observe the diffraction nature. The gap should be very, very small. And the other property is known to be interference. Interference means the superposition or the addition of two or more waves. In this case, we are going to see the summation of two waves. And to observe the interference nature of light, we'll use slits. Slits are a very gap or hollows, okay? Very small holes like this, so that it's possible to have a source and pass from these two slits and form an interference pattern. Actually, we have different slits. There can be single slit, double slit, triple, or multiple or gratings, so that it's possible to eliminate light and observe the interference pattern. As we have discussed previously, there can be constructive and destructive interference. As we have discussed in waves, two waves can be constructively interfere if they are in phase, or they might be destructively interfere if they are out of phase or anti-phase. In this case, let's take a double slit interference. For example, if you have a source from here, it's possible to cast those light and allow it to pass through two slits. And those slits will diffract, so that there is a diffraction nature of light. It will diffract here and here. And from this slit as well, it will diffract here and here. So that the light waves that are found here, around here, are going to be merged one another constructively and destructively, and there will be an observation of a series of light patches. There will be a brighter, darker, brighter, and darker, a series of light patches, and these light patches or bands of light are known to be fringes. We call them to be fringes. So the superposition of light beams will result a bright and dark light bands or parts known to be fringes. Dark fringes are known to be minima, also call them to be minima, whereas the bright fringes are known to be the maxima. The darker fringes are the result of destructive interference, whereas the brighter one are the result of constructive interference. In this case, from slit 1, there will be a wave like this, and from slit 2, there will be a wave like this. As they join here or superposed here, since they are in phase to one another, they will form a brighter spot, so that maxima is produced. And in this case, there might be a wave which is appearing from slit 1 and slit 2 are cancelling one another. They might be anti-phase, so that they will form a darker spot. This darker spot is known to be minima. We call them to be minima. And there will be central maxima. Then on the two sides, there will be a darker part known to be minima. So the central maxima, the first order minima, the first order maxima, and so on. These are formed due to constructive, destructive, constructive, and so on. Okay, this is what we call the interference nature of light. Actually, those nature appears due to the combination or the interference of two waves, and they will form a path difference and a phase difference. Actually, path difference means the difference of two waves in wavelengths, whereas phase difference means the difference of the two waves in measured in degree or radian. This is known to be phase difference and path difference. It's possible to correlate phase difference and path difference using this mathematical approach. This is what the path difference says. The path difference is equals to the phase difference in angle or in radian times lambda over 2 pi. It's possible to convert one into the other. Path difference to phase difference to path difference can be mathematically expressed using this. As we mentioned here, the wave propagating from slit 1 and slit 2. Here slit 1 and slit 2. The difference of the two rays, if the difference of the two rays is m times lambda, meaning the integral multiple of wavelengths, there will be a brighter spot or maxima is formed. Whereas if the difference of the two or the path difference is the ordinate multiplication, meaning 2m plus 1 lambda over 2. Okay, half of the wavelengths. If you have m is to be 0, you can have lambda over 2. M is 1. If you can have 3 times lambda over 2, 5 times lambda over 2, and so on. In such case, it's possible to have a darker spot or minima. So far, we have seen the interference pattern of double slit. It's also possible to observe interference pattern of a single slit, and a single slit forms central maxima which width is larger or twice as that of first order maxima. For example, the distance of the first order maxima is a and width of the central maxima is b. It's possible to correlate b as twice of a. Twice of the width of the first order maxima can be expressed twice as that of the first order maxima. And now let's try to see about the mathematical approach which was explained by Thomas Young and tries to find a relation between the wavelengths, slit gap, and the screen distance, and so on. So this is a very important law. Mathematically, it was very fundamental to prove that light has a wave nature. So the series of dark and bright spots found here can be mathematically expressed using this mathematical approach. Okay, so it's possible to find that the light which is coming from this and reach here, we don't know this, from central maximum to any part. It might be the first order maximum, the first order minimum, second order, and so on. So the distance from the central maximum to that of any of the pattern. For example, here you might have the third order maxima. Therefore, the distance from this to this is the difference, the path difference formed change in x, meaning S2 minus S1. It's possible to find this and propagate straight line so that you can find a mathematical relation, theta here. So sine theta can be expressed as the path difference between the two waves. As we have said that the path difference is integral multiple of lambda, there will be a maxima. And if it is odd multiplication of lambda over 2, there will be a minima. So that the difference, change in x, it's possible to say that sine theta is change in x over the distance between the two slits is known to be a slit gap. We call it to be slit gap, or we can represent it using S. And the other thing is it's possible to project and form an angle theta, so that tan theta is opposite over adjacent. The opposite one is the distance between the central maxima to any order, maxima or minima. And so that y over tan theta, when you express tan theta here, tan theta, say that y over d, where d is the distance between the double slit, and here you do have a screen. So that it's possible to have a mathematical approach. This is the general expression, y is equals to change in x d over s. But as change in x is m times lambda d over s, it is for maxima or bright fringe. Whereas as change in x is the odd multiplication of lambda over 2, it's possible to have for minima m plus 1 over 2 lambda d over s. It's possible to have such a mathematical approach. Y is always, remember that, the distance between the central maxima to any order of the maxima or minima. This is known to be Young's double slit experiment. And Young's double slit experiment, for his experiment, he used source. Here there is a color filter, single slit, double slit, as well as a screen. Thomas Young used color filter to filter out only a single wavelength. It's known to be monochromatic light. So produce a monochromatic light, Thomas Young used color filter. He used single slits so that there will be a sustainable wave pattern formed on the screen. He used a single slit. Then he used double slit to propagate and form an interference pattern. Then he used a screen. Actually, nowadays, it's possible to use laser for propagating those and form a coherent wave forms. And coherent source can be expressed as, coherent means the same type. There should be the same type of waves are interfering one another. The wave from this and this should be the same type. If it is light wave, this should be light wave. Sound wave and light wave cannot be interfered. So there should be a coherent source, and this is known to be the same type, and maintain a constant wave pattern or phase relation, so that there should be a monochromatic, unless there will be a different wave pattern and the phase relations are not going to be constant. Therefore, we mean coherent means the same type and there should be a constant wave front. And now let's try to see about a thin film interference pattern. So far we have tried to investigate about the nature of light, reflection, refraction, diffraction, and interference. Among one of the natural phenomena of the result of interference, one is in colorful phenomena known to be thin film interference. And thin film interference is a colorful phenomenon formed on splashed oil, soap bubble, and so on, as well as on rainbow. We can see this colorful phenomenon. And it is all the result of the interference of light from the two layers of the thin film. Okay, here you can have the thin film, might be soap bubble. The soap bubble has the higher layer and the lower layer. the reflection of the two lights, for example, here you have a source, as this light source cast on the upper surface, some of it might be reflected and some of it might be refracted and face the lower boundary. As well, it will be reflected back and as well refract. So the combination or the interference of these two rays, the rays which are reflected from the upper boundary and the lower boundary, will form the colorful phenomenon. This colorful phenomenon is known to be the thin film interference. And the thin film interference mathematically can be expressed, and one very important thing you should have to know is, as light is reflected from the upper boundary, for example here, the upper boundary has higher refractive. As light moves in air, its refractive index is like 1. And let's say that this is water, might be the refractive index of water 1.33. So it faces higher refractive index or higher refractive surface. As light reflected from higher refractive surface, there will be a 180-degree phase shift or phase change. Between the incident and reflected wave, there will be 180-degree phase shift, whereas as it is reflected from less boundary surface, it will be in phase. Okay, there will be no change if it is reflected from less boundary surface. So the combination of these two rays, reflected from upper boundary and lower boundary, will form a colorful phenomenon. And there will be a constructive and destructive interference pattern. The constructive interference pattern means that you can find the colors on each spectrum, whereas the destructive interference means among the spectrum you might miss one or two colors. For example, you might see red, yellow, orange. This might be the first order of spectrum. Again, you might see red, yellow. There will not be orange, for example. If you can't find, for example, let's say red, let's take blue and yellow, let's say. Again, you might find red, there will be yellow. You miss a blue color. If you miss one of the color, it means there will be a destructive interference on that spectrum. If you find a color, it means that there is a constructive interference. So on thin film interference, destructive means you miss some colors. So keep in your mind that, and it's possible to have a mathematical expression 2nt is equals to m plus 1 over 2 lambda for constructive interference, whereas 2nt is equals to m times lambda for destructive interference. Here, n means the refractive index of the film. The thin film might be made from soap bubble or oil puddles. So that's possible to find the refractive index of that. T is the thickness of the film. M, the order of the spectrum that you find, might be first order, second order, and so on. And lambda is the wavelengths of the light. For example, if you are trying to find red, previously we have said that blue is missed. Okay, so the wavelengths of the blue light in air can be given as lambda. Okay, and if you find red, for example, you can find the wavelengths of red in air. So lambda is the wavelengths of a given light in air, and know that n is the refractive index, t is the thickness of the oil. So this is for constructive and destructive interference of thin film interference. And at last, let's try to see about diffraction grating. Diffraction grating, so far we have tried to see about interference of single slit, double slits, and so on. Now let's try to see about the interference of multiple slits. Okay, as multiple slits are grooved on a single object, it's known to be grating. We call it to be grating. For example, here you have multiple slits, meaning within a centimeter there might be 500 or more than that number of slits or holes. So as light propagates through that slit, it will form an interference pattern. There might be different types of maxima and minima. Actually, it will form principal maxima and subsidiary maxima. For example, this is the interference pattern of single slits. This is the interference pattern of the double slit. As the number of slits are increased, it will form two types of bright maximas. Here, there is a principal maxima, and there is another smaller maxima, known to be subsidiary maxima. And as the number of slits are increasing more and more, there will be a brighter and very thinner principal maxima and a less brighter principal subsidiary maxima. For example, if this is the screen, exactly at the center there might be the wider principal maxima, then there will be a less maximas known to be subsidiary maxima, and there will be again principal maxima, there will be a very thin subsidiary maxima, and so on. This is what it says. As the number of slits are increasing and more, the subsidiary maximas are the intensity is very low and it's going to be very small. So this is how the interference pattern formed in diffraction grating. And there will be a mathematical approach for diffraction grating, and it says that sine theta m is m times lambda over d, where m is the order of spectrum. For example, here you have a device known to be the telescope. If you use a telescope or spectrometer, you are trying to observe the different colors from diffraction grating, so that exactly at the center you might see the white undeviated light. So as you bend this at some angle theta, you might try to find different colors. For example, you might see here red color at this instant, so that the angle theta is possible to find, and you might find red so many times. The first order spectrum, different colors, again you might find red on the second order of spectrum, and so on. So that, keeping this in your mind, on the first order or on the second order of spectrum, if you find an angle theta, it's possible to find sine theta of the mth order, meaning the first order spectrum or the second. Let's say in this case, this is the second order spectrum, meaning before that you can find red on the first order spectrum. Again, you can find red on the second order of spectrum. There are different order of spectrum, so that the sine theta of the mth order is possible to have m times lambda times d, where lambda is the wavelength of red in this case, and d is the space between each slits on the grating. Here d is the space between each slits, and it's possible to express this in meter. And for example, if you have the grating, let's say that the grating is 1 centimeter, and on this 1 centimeter you might have thousands or hundreds of number of slits. So the distance between each slits is known to be d. Okay, it's possible to find the d. For example, let's say that per 1 centimeter, here it says, for example, let's take a grating of having 5,000 grooves or slits per centimeter. So within 1 centimeter, if you find 5,000 slits, it's possible to find d, the length of the slits over the number of the slits. So that 1 centimeter per 5,000 gives us the slit gap, or we call it to be d. So the sine theta m's order can be given as m times lambda over d. Keep this in your mind. And at last, let's try to solve this simple example. Here it says yellow light with a wavelength of 589 nanometers strikes the diffraction grating with normal incidence, meaning perpendicular. So the grating slits have 5,000, as we have said previously, per centimeter. So at what angle will you see the light? Meaning you can find the order of spectrum to be 1. The first order of spectrum, you can see a yellow light on the spectrometer. So first it's possible to find d. We know that d is the length of the groove per number of slits, so that 1 centimeter per 5,000. And to convert it into meter, you should have to multiply it 10 raised to minus 2. So that 2 times 10 to the power of minus 6 meter is the distance between each slits. So we can find d, and m order of spectrum, the first order of spectrum. So from previous equation, sine theta 1 can be expressed as m times lambda over d. M is already 1, so that substituting all the value, we can find it to be sine theta 1 to be 0.2945 radian. It is expressed in radian, and you should have to convert it into degree, so that it is 17 degree. As you move your telescope or spectrometer at exactly 17 degree, you can find it the yellow color, or the first order of spectrum. So we can solve different examples and you can proceed on. So this is all that I've got for today. Next time we'll try to see about electrostatics. So goodbye for today.